Right. So, a very good afternoon, everyone. On behalf of the Alliance for an Energy Efficient Economy, AEEE, it is my pleasure to welcome the presenters and attendees to this webinar on sustainable cooling in buildings, accelerating advanced evaporative technologies and phase change materials. I am Ritubroto Sen, Senior Manager, Industry Engagement at AEEE, and I am joined by my colleagues. To my left is Bhairav Sharma, Deputy Manager, Membership and Training. And in front of me is Santosh Kumar Saini, Principal Research Associate at AEEE. I'll just present a couple of slides to give an overview about AEEE. So this slide that you see on your screen is a summary of what we do, what we are. Basically, we are founded in 2008, so which makes us about an 18-year-old organization. We advance energy efficiency as a resource and provide policy and implementation support to catalyze responsible energy use for a climate resilient and energy secure future. We collaborate with government, industry, and civil society organizations and drive policy research, innovation, and on-ground impact, targeting national and state level energy savings and GHG emission reductions. AEEE aims to be a dynamic contributor to make India one of the most attractive markets for the best available technologies to support this transition. We are a premier research body. You can also call us a leading think tank or an ecosystem enabler with programs running in multiple states across the country. At the bottom of your screen, you have as you can see, the number 70. So we have 70 member organizations from the industry, and many of them are involved directly or indirectly in our research projects, either as participants, as beneficiaries, or as contributors. So we are a member-led organization, and we consider that to be one of our key strengths. The RISE is more of an internal ethos and culture that we follow at AEEE, and the organization goals that we have are for this decade, and it is common to all the research projects that we do. So whether it is to facilitate green jobs or energy savings or investment, these are our broad high-level goals that we try to fulfill through all our research projects. So when I speak of research projects, we publish research reports, white papers, syndicated research. We also take up CSR projects. We do a lot of capacity building exercises. We do policy implementation support, stakeholder consultation, peer reviews of report. We facilitate industry visits, technology evaluation and deployment of pilots, and so on. Now, in terms of research projects, these are the 5 major verticals that AEEE works on. Very quickly, if I have to run through what each of these verticals does beyond what you see on your screen. So under buildings, which is our largest team, we kind of help finance and deploy retrofits for existing buildings via innovative business models. We also push for wider use of low embodied carbon materials and circular building economies. Under sustainable cooling and refrigeration, where we are trying to meet India's heat challenge sustainably, we promote R&D in low carbon cooling technologies, and probably the 2 presenters that we have today will fall under this particular vertical especially. And we also push for performance standards, labeling, and efficiency reforms, norms for refrigeration and air conditioning. Under cold chain, we look at driving modernization of cold storage infrastructure via retrofitting, efficiency upgrades, and new low carbon systems. We also support policies that subsidize or incentivize efficient cold chain units. Under smart and resilient power, we work especially for resilient grids. We promote demand-side strategies, especially demand flexibility, to reduce dependence on fossil-based peak supply. We also push regulators, that is various DISCOMs, to create tariff structures that reward demand flexibility and enable more dynamic pricing. We also develop business models for demand flexibility services. Under sustainable mobility, which is kind of sustainable transport, we promote integrated clean mobility, combining electric vehicles, hybrid vehicles, and we also build capacity for adoption and maintenance of green mobility solutions across urban and rural areas, one of which is conversion of ICE vehicles to e-vehicles. The global and local action is primarily our work with various government, especially at the central and state level. Our projects are ongoing in multiple states across the country. However, our flagship initiatives include the energy conservation building code, supporting the development of that code and implementation of that code, supporting again the India Cooling Action Plan, which was led by MOFCC and powered by AEEE. And every year, along with the Ministry of Power and the Bureau, we launch the State Energy Efficiency Index, which is a ranking of states in terms of their enabling policies. All of this initiatives gives us a very close connect with the industry and the government departments. The decarbonization catalyst is a cross-cutting vertical. It supports all the other four verticals that I spoke about. So whether it is financing model, blended finance, or ESCO, or sustainable procurement guidelines, or data analysis, benchmarking, or capacity building training programs, all fall under the above four verticals. The small icon that you see on the bottom right of your screen is the PMVA training that we administer in India, and it is particularly relevant, of course, for all energy efficiency professionals, but especially for MNB, those working in the MNB sector. With that, if you also visit our website and follow us on social media, you will get access to many of our research reports and know in further detail about our initiatives. Finally, about today's ION Zero webinar series. So this was something that we had launched last year, and this is the 8th episode under this series. ION Zero offers deep dives into critical solutions for achieving net zero. The episodes in this series cover 4 thematic areas: latest product and technology innovations, breakthrough financing models, evolving regulatory policies, and emerging career and skilling opportunities in the net zero ecosystem. So under today's episode, that is the 8th episode under this series, it will be delivered by the 2 veteran industry experts from 2 leading AEEE member organizations, as you can see on your screen. So Sandeep ji, Kapil ji, all the attendees have read your bio. So while registering for this webinar, so I would request yourselves to say something beyond that in terms of what you and your organization does and what kind of impact it is having. And I will probably be allowed to, give you about a minute or so each of you to give a brief introduction about yourselves. Over to you, Sandeep ji, if I can request you to go first.
Yeah, thanks, Ritabrata ji. So before that, I just want to know, there were some messages in the group that there is some echo. Is it still there? Can someone put in the chat? I heard read.
Try to resolve that. We will look into that, Sandeep ji, but your voice is loud and clear, Sandeep ji.
Yeah, I got the message that it is clear. Thank you so much, Ritabrata ji, once again. And thanks to Bhairav ji and Santosh ji. And thanks to AEEE for giving me this opportunity, me and our organization. So if I briefly tell you about what our organization does in a minute, basically we are pioneers into indirect evaporative cooling, which is one of the few technologies which are categorized as not in kind technologies, means that they are not much in use, but they have a great potential. So when I talk about indirect evaporative cooling, basically there are for cooling, there are 3 streams, basically 2 streams earlier. One was the air cooling, which has existed for thousands of years. But the air cooling had the problem that in the monsoon, moisture created an issue and the comfort level was not there. That's how the air conditioning was invented in 1902. And this technology, which I'm talking about, is a basically advanced version of evaporative cooling technology, which takes care of the problem of the evaporative cooling, that air and water don't get mixed directly. So the moisture level, the moisture content, the absolute humidity doesn't go up even in monsoon. And I would say this is the third stream of cooling, apart from air conditioning and evaporative air cooling, single stage. And it's gaining momentum, especially now in industrial, but it has a big scope in commercial also in coming years. Thank you so much.
Thank you, Sandeep ji. Kapil ji, can I request you to take a minute and introduce yourselves and your organization?
Sure. Thank you. Thanks, AEEE, for giving us this opportunity to come and talk about the products related to sustainable cooling. So phase change material is the one I will be talking about. But if I need to just give you background about, myself and BP RefCool, we work mainly onto the thermal, materials. So Say, for example, we work on phase change material, we work on heat transfer fluids, we work on refrigerant management. So whether it is leak detection technologies or it is recovery technologies. So, I would say, in 2015, when we started this company, BP RefCool, we started focusing on areas which are probably left out, not much, technically worked in India. So we started picking them one by one, and fashion materials we entered after COVID to innovate and bring new face change materials to the market, which beyond uh, risk mitigation. So earlier it used to be considered as, when if power goes off, my system should continue to give cooling. So phase change material was used primarily for that application, but now it is more to do from risk mitigation to energy optimization. So that is where entire BP Ref Pool is working on sustainable cooling and heating for all.
Thank you, Sandeep ji. We thank you for your time and support to AEEE and for joining us and help educating ourselves as well as our attendees today. Speaking of attendees, we have now close to 70 attendees, so it has picked up as time progress. So, dear attendees, thank you for joining. We encourage this webinar to be as interactive as possible. We will try to take up all your questions either individually or by clubbing with other questions. So in this regard, we request you to put all your questions in the Q&A box that you have in your screen. Any kind of connectivity or hygiene issues that you face, you can put it in the chat box. But otherwise, questions that you have related to the presentations for our speakers, please put that in the Q&A box. With that, I invite our first presenter, Mr. Sandeep Kohli. His topic is Advanced Evaporative Cooling Technologies, as you just heard. So with that, Sandeep ji, I would request you to share your screen and present. You will have 25 minutes, and I will probably ping you at the 20th minute to give a 5-minute wrap-up. Over to you, Sandeep ji. I'll let you know once your screen is visible.
So is my screen visible?
Yes, it is.
Okay. So thanks once again. I will start my presentation. So as I told initially also that we are pioneers into indirect evaporative cooling technology, which is an advanced version of evaporative cooling technology, which has existed for thousands of years. So one issue with evaporative cooling technology, where in monsoon, the moisture level, absolute humidity was going up because air and water were getting directly in touch. We have taken care of that with the help of our patented heat exchanger, which we name DAMA. I will show in subsequent slides what is it. So I will go through this presentation. So basically what we are saying is that we have to not apply air conditioning all the time, or we don't have to apply only air cooling at all the times. There are different technologies available like this indirect evaporative cooling, which can be applied either alone, standalone, or in hybrid mode to save on energy, save on use of refrigerants, and lower the greenhouse gas effect. So with that, I will just proceed with my presentation. So I will just go through the initial slides where most of you know, but I will still try to say that why cooling was required, because it was to promote the health, improve the health and productivity. And there are some studies done by some global payroll alliance, which is basically you can see in the below line. And that is the reason for this slide, that this is where cooling was required. So this is why cooling is important. So when we talk about cooling, air conditioning comes directly into mind, because air conditioning, although invented in 1902, but it is now well versed in India. Most of the people know about it. The unit is almost standard size, and everyone talks about AC easily. So why AC? Basically, because global warming is happening. 2024 was the hottest year, and urbanization is also happening. So urbanization, you need more houses, you need air conditioners to get the right temperature, and population is also growing. People, currently it is expected to be 9.7 billion. Currently it is 8.2 billion, and it is expected to touch 9.7 billion by 2050 and subsequent. And cooling tonnage demand has also grown 8 times going to grow in 8 times from 2017-18 to 2037-38. So this is going to be a big task. Now with this cooling, there are some challenges which come. So if we go on with increasing the air conditioning as it is, window AC, split AC, more of air conditioning, then there are challenges like electricity consumption surge will be, of course, be there, because air conditioning uses a lot of energy, almost 40 to 45% of the building energy. And demand for electricity will triple by 2050. So we need to have that kind of electricity production. And data centers are coming up in a big way. They will also require a lot of air conditioning. And compounding facility costs, HV systems account for almost 40%, as I said. So the billing in energy cost will go up if we go as it is. And this is the money cost. Now, what about environment? Now, as the topic is, we are talking about sustainable cooling. So with if we go as it is, like air conditioning, then cooling gas, greenhouse gas emissions are soaring. So it is making the earth more warmer, as most of you know. And HFC reference leaks are also creating a climate bomb, hidden climate bomb. They are creating a lot of issues. And ozone and climate crossover are also challenges. So these are the environmental challenges which cannot be now neglected, because the time has come that apart from the material or the money cost, we should look at as a human being, because there is one earth. So how do we take care of that? So for that, we have to rethink about comfort and rethink about cooling as it is. Basically, earlier, if you see the red diagram in the building, that was the earlier concept of very small area where we said that this is the area where this is the kind of humidity, temperature, fresh air motion. But with the air cooling, this holistic comfort and thinking, we can expand that area and we can bring more technologies. We can think about increasing the airflow to get the same effect, because ultimately heat is mass flow rate into delta T. So if we can increase the quantity of air, we can get away with the higher delta T. And that's where the indirect evaporative cooling comes into picture. So I will just say evaporative cooling, most of you know, you must have used desert coolers in your home sometime earlier, if not now, today. So it is basically, we pass the air through a pad and the water is falling, then hot air gets the evaporation causes the cooling, and water gets evaporated by taking the heat from the hot air, and the air becomes colder in other way. So now what is the difference between the earlier kind of direct cooling, which we called, or the desert coolers I was talking about, and this indirect? If you see the photograph on the left side, that is the direct cooling, the cellulose poet. So if outside temperature is, say, we have taken the examples of Ahmedabad, and we have followed ISA 7896-2023, which is the current standard for weather for Indian weather data for Indian cities, which is developed in collaboration with ISREC. So for Ahmedabad, in summer, outside DBT is say 42.7 and WBTC is 25 as per this data for 0.4% conditions. Then from direct evaporative cooling, you can come down to 26.8 degrees C, as you can see, DBT, and 25 degrees C WBT. So this is because for single stage cooling or the adiabatic cooling, you cannot go below the wet bulb. Now the beauty of this indirect evaporative cooling is, as you can see on the right side, that for the same outside ambient conditions, you can achieve a higher DBT, but you can go to a WBT which is lower than that. Was not possible earlier. That's why the air conditioning was invented, because the problem was more of a moisture. And I will show in the later slides how from 28.5, by adding another part of direct evaporative cooling, which we call indirect direct, we can go to lower temperature and lower WBT. That I will show in the next slides. So here is a comparison on the cyclopetic chart between direct evaporative cooling and indirect evaporative cooling. So you can see it is all there. In direct evaporative cooling, if you see the fifth line, moisture grain, there is an increase. But in indirect evaporative, there is no, it moves on constant moisture grain line, or the absolute humidity line. So there is not a single drop of moisture addition, but the air gets cooled. So what are the benefits? Why we are talking about this today's seminar? What is it for you? So basically, indirect evaporative cooling can reduce your cost, energy cost up to 70%, and environment cost is zero. Cost is zero because there are no refrigerants. It's water is a refrigerant actually, and human and health cost because it's 100% fresh air most of the times, so you can get better health. So all these benefits you can get from indirect evaporative cooling. So I will talk about some products. This is the indirect tube. This is the heat exchanger, which looks like DAMA. We call it dry air moisture. This is our patented heat exchanger. And this is about it. This is the heart of the system. Now, based on this entire, most of the products are made. I will show in subsequent slides. So it saves up to 70% energy over conventional AC. So you can just, we have calculations, we have case studies to prove that. And it essentially cools the airstream. It's a low weight. It's a basically polypropylene paper-based heat exchanger, not of metal. Although the box, of course, the sides are of metal, but inside it is a polypropylene paper-based material. And it's a long life. And we have patent for this product in USA, Australia, and India. Now we are proud to say that we are the first company in world which brought this technology into product shape. We have Green Pro for all the products, and we have a type tested report by ASHRAE third party. So now how it works? There are actually two airstreams. And there are heat exchanger. There are two paths. One path is basically having the secondary air from bottom to top. You can see, and from left to right is the main primary air. So they are moving in different channel adjacent to each other. So what happens? The air goes, which secondary air takes the moisture and gets cooled, and that cooling is transferred to the primary air. So there is no direct touch of moisture for the primary air, but the primary air gets cooled by the cooling of secondary air. And the secondary air is cooled by evaporative cooling, of course. And as you can see, I've shown in the earlier slide also in the bottom left, for ambient of Ahmedabad in summer, from 42.7 dBT, 25 degrees C WBT, we can reach to 28.5 dBT and 21.1 WBT. Here, water is the refrigerant. Now, based on this heat exchanger, we can develop a lot of products. I will go into products one by one. One, of course, is HMX IDEC and 3-stage units. There are two products basically. We'll discuss separately. Then normal TFA doesn't have DAMA. We have a TFA with DAMA and coil. So that is HMX TFA, we call it. And then we can have AHUs also. With return air also, we can give you the normal AHU. Instead of normal AHU, we can have a return air AHU with DAMA, which can also save energy. So all these products I will discuss in brief one by one. First and foremost is the basic product. If you can see, this is the brown portion is basically cooling pads which are there in single stage. The gray portion just behind the brown portion is the DAMA, and the blue are the lures basically to stop the water from going outside. And then filters and fans are generally there. So now this slide is very, very important. When you have seen that from IDEC, although we can go into WBT less than the WBT of the atmosphere, but DBT was slightly more than the DEC. So what we do, we have made a product where we combine two, we call it IDEC. So indirect, direct evaporative cooling. So we first do indirect evaporative cooling, once we shift the WBT from 25 to 21.1, then we do the direct evaporative cooling on the constant wet bulb line. And then that's how we can achieve, finally, if you see the IDEC outlet, we can achieve a temperature of 21.8 degrees C and WBT of 21.1 degrees C in summer in Ahmedabad. Now you imagine, sorry, for summers, we can 22 degrees generally considered as air conditioning temperature, but we can achieve 21.8 by not using any refrigerant, any compressor, any chiller, just 100% fresh air, one through system. And even the moisture added is 58% lesser than the evaporative cooling, which was the problem with the evaporative cooling. So this is the beauty of the system. In summer, in dry areas, it works as good as air conditioning. That's why in countries like Saudi Arabia, we have places like Riyadh, where they are thinking of replacing they have got the opportunity to hold a World Cup in 2034, and they are thinking of going for indirect evaporative cooling in a big way. And we are in touch with them. This is how the unit looks like. This is a better diagram to just show. As you can see, 40.2.7 dBT on the left side and WBT of 25. We have gone down to 28.5 and 21.1 WBT through the DAMA. And then after the cellulose pad, the final outcome is 21.8 degrees C DBT and 21.1 degrees C WBT. So that's the beauty, that we are able to reduce the WBT without use of any refrigerant, any chiller, any compressor. That's a lot of energy saving. Now, this is again a very important slide. We have done study for 8760 hours for cities like Delhi, where we are currently sitting. I'm in Delhi right now. That's how the AEEE and Kapil is also there. So Jaipur, Ahmedabad, Pune, and Hyderabad. If you see on the left side, the IDEC outlet temperature, there are different rows. For less than 20 degrees C, if we consider 5 degrees C delta T, the room temperature of say 25 degrees C, for 4986 hours, almost 57% of the time in Delhi, you don't need to run an AC. If you are okay to maintain 25 degrees, of course, with the higher airflow, because that's how you get the better field temperature. So almost 57% of the time you don't need AC, and that's how the hybrid system will work. So you can actually in Delhi, like in city in like Delhi, you can for 57% of the time you don't need to run an AC if you're okay with 25 degrees C, which is the new temperature as per the comfort guideline, new revised comfort guideline, because you can increase the air volume and get the same effect which you can get at 22 degrees C, and a lesser air which is thrown by the AC. Now, if you as you go down, so see 26 to 31 degrees C, basically for industries, almost 93% of the time we can do away with the air conditioning. We have done a lot of industries inside in central India, now in North India also we are doing a lot of. But now you go to Pune, just see the Pune. For Pune, if you are okay with 29 degrees C temperature in room, 98% of the time in year, you can do away with air conditioning. No air conditioning required. And I will show the case study of a working building, Enpro in Pune, in subsequent slides, where they are running throughout the year on our system, and that building is a gold rated IGBC building. And for cities like Pune, Bangalore, even for that matter, Hyderabad, you see Hyderabad also, almost 99% of the time, if you are ready to base around 29 degrees C with higher airflow, of course, then you can do away with air conditioning. This is the study. We can help you with the specific cities. We have the softwares and all that. Now, this is the case study about which I was talking, Enpro. Beautiful. This case study got the best case study award in Cool Conclave exhibition last year at Indore. And we also got the award for best decarbonization product and company supporting decarbonization. So you see that all the details are there. If you can see the table, it's a combined, because there are some conference rooms where they need the air conditioning. So if they had gone for only air conditioning, they would have required 249 kilowatt of connected load. But with our system, it was 150.8 kilowatt. And the average operating load was 105.5. So there is a saving of almost 68.8 kilowatt per hour. You can imagine how big this saving is for a building, 6-story building, a small building. Well, it's in the sense that there are big commercial buildings. This is a commercial building, by the way. And this is how the unit looks like, the exact the unit picture on the rooftop. And we saved a lot of CO2. You can see almost 48,779 grams or 48.77 kilograms of CO2 per. So we are really helping in decarbonization the world. And this is this case study is a great example of that. Another is in Pune again, a big car manufacturer. This is Volkswagen actually, by the way. And we have installed almost 34 lakh CFM. And they are doing indirect evaporative cooling. The German company, when they came into India, they were confused whether to go for air conditioning, but air conditioning means a lot of energy consumption, lot of power bills, and air cooling was not serving the purpose. Then we came into picture and we designed the system. We have the capability to design the system also. We can become a sort of consultant for the consultant or for the end user. And then we suggested this, and this is running for almost 10 years now. And this is one of our biggest installations in India. The complete factory, I've been to that factory a couple of times, and it's working. It's 100% fresh, cool air. You feel better, and the temperatures are almost all the year in bearable range. Now, 3-stage. So there are few places, as you said, saw that in Delhi we could achieve around 70%. For what about for remaining 30%? So what we do, we have a 3-stage unit also. We can add a cooling coil. What will happen? The cooling coil capacity will reduce because we have already pre-cooled the fresh air. For summer, you didn't. If you see the blue line in the bottom, you don't need to run the chiller or the coil. But in monsoon, you see the red line. For some part of some cooling will be achieved by the cooling, but the cooling coil capacity will be very small. So this is a hybrid unit. The hybrid unit is the demand of the time today. We cannot blindly just put the air conditioning everywhere, whether it is required in some seasons or not. We have to have hybrid system which will save you lot of energy. You can see the calculations on the left side. So unit outlet in even in humid working below table is 19.6 degrees C TBT at 19.1 degrees C WBT. If you had gone for complete air conditioning in this, your cooling coil capacity, the chiller capacity would have been huge. This is how the unit looks like. It's basically DAMA with cellulose pad and coil and water samp, and this is all three stages are there. If you see fresh air in 35 degrees C, post indirect is 30.6, and then we can go to 21.2 and WBT of 20.5. We have done these three stages in many companies like Bosch as an example in Bangalore. And then we come to hybrid HU. We can take the return air also. So there are sometimes it is the fresh air requirement is very less, especially in some office buildings or some areas. So we can have it return air HU with DAMA, and that also saves you a lot of energy. This is the comparison we have done for our HU versus conventional HU. For 9 to 18, 18 is 1800 hours. Basically, it's 9 a.m. to 6 p.m. Operation of a 10,000 CFM unit. You see the kind of savings in various cities. Ahmedabad, Jodhpur, Indore. This is for 10,000 CFM. This is the saving of energy. So there is a lot of potential to save energy across India in many cities. And this institute in Nimli is an example. It's a quite old installation, and we have installed hybrid HU of 66,500 CFM with 60R cooling coil and IDEC of 26. So time is for hybrid. And this next product is hybrid TFA. So if you do the cooling with normal cooling coil, you have to cool it from 40 to 60 degrees C, 16 degrees C. The requirement is of 4.6 TR. But if you go with the IEC TFA, which I will show you the secondary chart, the requirement is only 2.5 TR. So you are saving 2.1 TR per 1000 CFM for cooling from 40 degrees C to 16 degrees C. You see how the blue line is representing the IEC. So your cooling coil capacity gets reduced. So hybrid is the demand, is the need of the hour. And I will request all the attendees of this seminar or webinar to propagate and to talk about it so that the right technology or right things are placed in future projects. This is how the hybrid TFA unit looks like. And savings again from 9 a.m. to 6 p.m. You can see a lot of savings in Jaipur, 24%. There the city, the more the savings. Indore, 24%. Nagpur, 19% savings. We have done Goldman Sachs in Bangalore with this, and this building in Sharjah, UAE. Now, this is a small calculation. I will not go too much into detail because time is not there. But you can see there are three methods by which we do the heat load by formula of Q is equal to RSH, sensible heat divided by this factor into delta T. Then we also know the air changes. Sometimes we check what are the guidelines of ISRE for air changes. And then we have some thumb rules because we have done so many installations. So from all these three, when the highest we take, so that even if we took highest, the power consumption or the requirement, energy savings are still huge. And duct designing, I will not go too much into detail, but we also suggest on what kind of duct designing, because these CFMs are higher in evaporative cooling than air conditioning. And these are some standards like basically sheet thickness and all those things. We are all units are our Green Pro. And although there will be frequently asked questions, there will be questions in the Q&A, but there are few questions which I thought I should answer. So water quality recommended is TDS below 500 ppm, hardness below 100 ppm, pH between 7.5 to 8.5, and maximum allowable TDS inside machine sump is 1000 ppm. Filter cleaning on weekly basis because water is there. Water quality is an issue in some parts of India. So we can install TDS controller also, which automatically drains and the pipe and takes the new water whenever the TDS level goes up. We have done this kind of system so that it's automated. You don't need to always worry about it. So I will just rush through worldwide references. So we have India, we have Africa, we have this UAE, we have Jordan, we have Egypt, we have Spain, we have Japan, Thailand, Australia. We were the finalists in the global cooling prize for this technology. Total installed CFM is more than 1.2 million. So, sorry, 12 million, my mistake. And these are few photographs: ABB Baroda, Amazon Nagpur, Apollo, all big companies, Center for Science and Research, Indian IIT Indore, Infosys Jaipur, and in UAE, many installations are there because at Saudi also. And this is our own office in Pune, and Akshay Patra and Vrindavan, Nasik, MES Hospital in Thalsedam Bhavan we have done in Delhi with our units. Hindustan Aeronautics Limited, TerraSpin, our own facility, Tata Motors Ahmedabad, Volkswagen Pune, I have discussed. And if you see all the big brands, be it Apollo, Auto, Volkswagen, Seat, foods we are doing Haldiram's, food processing and all this. Then commercial building, Godrej, Adani, Bosch, Goldman Sachs, and Google, Intas, Pharma, Intas, print and packaging also. Engineering में ABB, Bosch, GE, FMCG में RTC, Barico, Himalaya, and textile में also we have done. So all big names, Flipkart of course in warehouses. So basically, we are a trusted brand. We have 120 million plus. Sorry, it's not even 12. It was 120 million. This million thing confuses sometimes. We are more attuned to crores and thousands and lakhs. Sorry for that. So 120 million plus CFM. World's number one in indirect evaporative cooling. 86 plus. Our group is 86 plus years old. All this company, this business unit is almost 28 years old. But our group is basically textile engineering. This is the group. Basically, we do a lot of cooling. Cooling is done in HMX and safety, and there's an Axis valence, and textile is our main product, main line, which is there for 86 years, and precision compounds for TerraSpin, and wastewater we have collaboration with Huber of Germany. So we do wastewater for that. So my email ID and the mobile number is there at the bottom of the slide. If there are questions, we will, of course, I will answer, and if there are longer answers required or you need to talk to us independently, you can note down this email ID and mobile number and you can get in touch with me. So with that, I think I have taken a little more time, but I've tried to make it as fast as I can.
Thank you, Sandeepji. You can stop sharing your screen.
Okay, I think it's stopped now.
Yeah. No, first of all, thank you for the wonderful presentation, and even more for finishing it bang on time. You haven't taken more time at all. So we will have the entire 5 minutes that we have allocated for the Q&A, and for that, I'll request my colleague Santosh to take it up, whatever questions we have from the audience. Over to you, Santosh.
Sure.
Thank you, RBS. Actually, I think two questions.
You are on mute. Somehow you went on mute. I'm not able to hear.
So now I hope you can hear us. So I think 2-3 questions you already have taken, Sandeepji, and a few questions I can see on the box is that one is asking that how DAMA is different than other indirect evaporative cooling systems available in the market for buildings and in the textile industry. So a comparison, if you can show or present, that will be.
So basically, as I said, DAMA is a patented heat exchanger which we have developed. So this is basically a heat exchanger with their one channel is water, the other channel is air. Parallelly, they are going. And basically, we are the pioneers who developed this because there is a lot of R&D and lot of angle, what angle we have to bake, what kind of pores sizes we have to do. So there are few companies who have also come up with a similar heat exchanger, but difference I would say is basically we are the pioneers. We have the experience. We have done R&D. We have running applications, and the ones who have come in the market are new ones. They are just trying to do some by hit and trial, whereas we have got the patent for India, Australia, and US.
One question is again a comparative question only. So that asks like for a 1000 CFM IDEH, how much is the water consumption due to the evaporation and the power comparisons as well. If you can present also. Just do that.
So water consumption, of course, depends on the city because rate of evaporation at and also at the time of that. So for this water evaporation, we can get if you can, the person can get in touch with us with the city and the if it is for the throughout the year, then we can give a detailed data.
One more question is how is this feasible for tenant occupied or core and cell buildings where the tenant is installing the HVAC system when compared with the high efficient VRF system? So I think
So one thing in the last answer, I would just like to add one more thing for the person who had asked. So we have done a comparison for a particular city where we have found that our consumption of water is around 2 GPM per ton. If you consider the sensible load we are able to cover, that if you convert it into tonnage, then around 2 GPM per ton is what our requirement is there. But having said that, it is too general. For a particular city throughout the year, it depends on the temperatures of that city for the 8760 hours, and then we can give the exact water requirement. Sorry, you can repeat the next question. I just didn't listen to it. The question which you just asked.
so that is like if it is the technology is feasible for tenant occupied versus the normal VRF systems where the centralized or that cooling system is there. So if tenants want to install this individually, how that will be possible or feasibility?
So we have yet to come with a product which is for light commercial or residential sector. Currently, what we have are the bigger machines which are for at least a building or a floor of a few thousand square feet. But having said that, we were the finalist in that the global cooling prize, and that product which we propose as a we are in the process of working on to bring it in a market as a commercial product. It's yet to come from our side, but seeing the requirement of this and many people getting attracted to this kind of cooling because it gives freshness also, we'll soon work on that and come out with something on that.
Maybe two more questions. So one is that for the data centers and hospitals, how this system is beneficial, if it can be used directly or not, and what is their feasibility. So for both applications like data centers, these are the emerging applications in India, and again in the hospitals where high air changes are required, how this makes a difference there.
So hospitals, it can definitely be used because we have 3 stages, so we can reach any temperature because like an HU can reach say cooling coil outlet temperature of 12 degrees C or 11 degrees C, we can also reach. In fact, we will save on energy because our inlet temperature to cooling coil will be lesser because we would have already pre-cooled the fresh air. And in hospitals, more fresh air is required, so it's all the more important that we have hybrid HUs instead of the normal HU in hospitals. And we can have any kind of filtration, so that is not an even HEPA filter. We can go up to 200 mm static overall, so that is not an issue. It's basically you can see it's an HU with DAMA in it, which will save you a lot of energy by pre-cooling the fresh air. And you don't need to have the return air also because there is another technology called heat recovery wheel in which you can also reduce the fresh air load, but you need to bring the return air also to the unit, but that's not requirement here. It's basically if you are not able to bring the return air, it's not an issue here. And regarding data centers, yes, we are working. Data centers requirement have now, earlier they were not supporting evaporative air cooling, but now they have understood and the technology has improved. So we are working on that also, and we will soon come out with a product for data centers also.
One more, maybe the last question is already you have presented the comparison between cities, that how the system efficiency will be and what all the conditions we can achieve. But there's one question that in the coastal regions where the conditions are warm and humid, how this will be, if it will be a feasible solution there, like in Bengal or Kolkata-like conditions where humidity is high and the temperatures are a bit warmer. So what will be the comparison over there? How many hours we can use this, if we can use or not? So please comment on that as well.
So, question is good. I think in coastal cities we have not made that comparison. Most of it was central or part of India. But if you see our installations, we have installed in MRF in C8 in Chennai, which is a coastal city, and we have installed in many other coastal cities also. Now the challenge is in coastal cities, the savings will be lesser because, as I told, indirect evaporative cooling doesn't add moisture. But having said that, if you require a temperature of 20 degrees, maybe still in hybrid HU, the cooling coil will be bigger than what it will be in a city like Indore or Pune. So we can save, but it has to then make a sense. We have to calculate the payback period, whether it is a industrial, because industrial is easier to do because they can maintain with higher temperatures. So they may not need the cooling coil at all. We have done C8 and MRF in Chennai. But comfort applications, we need to come out. We can do that, but will it be feasible? Will it be cost effective? How much will be the payback period? We need to case basis. We need to check.
Maybe one more interesting question, and that is about the retrofitting the system. Like, if we can retrofit and use this DAMA system in the existing HVAC systems directly, and what will be the feasibility over there?
So, see, DAMA has a pressure drop of some 15 to 16 mm. So, if your fan has that much static, and then you need a space also. So, retrofitting, as it is, it's a difficult situation because I've been in the HU industry. Space is always less. HU is already quite compact because you need to have some kind of section also for say 700, 800 mm, and you need to have static available in fan to overcome that pressure drop, which will be through DAMA. But having said that, fan retrofitting is also an option. So if we can replace the fan along with this, because now more efficient fan which are available, let's say, and then if we have space, we can think about retrofitting.
So I think thank you, Sandeep, for answering. There are a few more questions, but we request participants to.
For a few more questions, Sandeep, what I would request you is when Kapil presents, if you could just please look at the Q&A box, and if we have tried to cover most of the questions, maybe you could type out very short, brief answers to them if you can.
Sure.
Thank you. I mean, the very fact that the audience was so engaged goes on to show how much they have engaged with your presentation. So over to you, Kapil again. Same house rules, 20 minutes. I'll ping you and request you to conclude at the 25th minute so that we have another 5 minutes for Q&A. Please share your screen and initiate a presentation. We can see your slides. It will help if you go to full screen mode.
So you can see the full screen now?
Now it is in full screen mode. Go ahead, Kapil.
Perfect. Great. Thank you. So 20 minutes for this topic after Sandeep Kohli is difficult, but let me just try to do it.
25, sir. 25
minutes. Yeah. So, when we were talking about, or Sandeep ji was talking about evaporative cooling, we are talking of phase change. We are talking about liquid to vapor. So there also the phase change happens. So if we need to understand the phase change, how it works, and how it impacts or where the opportunity lies, we'll go to some basics. Say there are 3 phases of matter. So gas, liquid, solid. Now, if the phase change is happening between gas to liquid, liquid to gas, this is essentially what happens in our refrigeration air conditioning, simply vapor compression system, where in evaporator, the liquid evaporates, makes into gas, and in a condenser, it condenses back to liquid. So if we use that, we are already using it. Now, this is also used in thermal storage or, other cooling methodologies where compressor is not used. So this cooling of liquid gas or gas liquid is normally called as 2-phase cooling instead of phase change material. So phase change material, if you hear in journal in market, essentially we are talking about solid liquid, liquid solid. Because in solid liquid, liquid solid, almost the volume remains constant. There would be some change in volume, but not much. So that's how you can accommodate the same material in two different forms within the same container, packaging, or volume. So that makes it different, and the amount of latent heat certainly is much higher. So that is how phase change materials and two-phase cooling. So two-phase cooling, if Sandeep ji was talking about data center, and there was question about data center. So if you talk of data center, so data center use air for cooling, data center use liquid for cooling. Liquid is one phase, single phase. So cold liquid comes in, hot liquids goes out. So that's how one phase cooling. And then there is a two-phase cooling where the liquid comes in, it boils off, evaporates, vapor goes out, it condenses back and returns back. So in data center, liquid gas liquid is used, solid liquid is also getting used. We'll talk about later. So yeah. So when we talk of phase change material, the easiest example comes in our mind to explain is water and ice. So when you change phase of water in your refrigerator or a freezer, that's essentially when the phase change is happening. So if you put it in, at 25 degrees centigrade, it quickly comes to 0 degrees centigrade. And at 0 degrees centigrade, it completely freezes solid to ice, complete ice. And then further it goes down to the whatever is the cabinet temperature of -40 and -20. So that is essentially what happens is, so the lot of time which is taken is at constant temperature, which is 0 degrees centigrade for water. Now, we use water as phase change material for a lot of years. So, if you need to transport anything, you would freeze ice, put that into a bottle or bag or something and transport. And then, yes, you can certainly use that cooling, because melting of ice, even, when you are using drinks, and in drink you put a ice cube, essentially you're not trying to dilute. What you're trying to do is maintain the temperature for long. So that is what this phase change material does. Now, if you can use 0 degrees centigrade, probably water is very good phase change material. But if you don't want 0 degree, if you want lower than 0 degree or higher than 0 degrees centigrade, and you want cooling or heating to be retained at that temperature, that is where different phase change materials comes in. But when these different material comes in, we need to understand that probably they may not behave as water. Now for water, the freezing and melting points are same, 0 degrees centigrade. So you put it in a -5 degree freezer, it freezes. If you put it into a 0 degree freezer, it will be very hard for it to freeze, because there is not going to be temperature change. So what you need essentially is, you need a material which you need a temperature at which there is a heat exchange happening, and the freezing and the melting can be utilized. Now, if you take an example, this on your screen is a example of -19 degree PCM. Now, if you see, if you can see my mouse moving, if you start to freeze this PCM, it will first come down to say -18, -22 or something, and then it will start to freeze and goes up. So this is called subcooling or supercooling. This is very critical for most of the phase change material. So a lot of time we receive a lot of calls from customers that, hey, I want to use phase change material for building, for helmet, for cooling vest, for so many other applications. If you are evaluating any application, you need to figure out what is your freezing temperature, what is your melting temperature, and these can be different. So if we take this example, yes, it freezes at 90 -19, but first it need to reach -21 or -22. If you don't reach, it will not freeze. So that is where it becomes very critical for you to understand the freezing and melting cycle of both phase change materials need to be understood before applying it into the application. So this is one. So then the amount of latent heat. So in case of water, if you see the line was absolutely straight. Here you may not see straight, so there can be a deviation. So there can be a drop in temperature while freezing, and there can be a rise in temperature while melting. So this is what you can expect, and these technical data sheets are available when you are selecting any phase change material. And most of the phase change material will give you enough properties for you to evaluate and calculate how much quantity, say, kilojoules per kg is the latent heat which is available. So how much it can be used for what number of hours of backup and all that stuff. But it need to be thoroughly understood that the freezing and melting curve are different, and then you need to take care of. If you understand all these, then yes, what you need is to calculate how much energy it absorbs and how much energy it releases. Now it absorbs at certain different temperature, releases at certain different temperature, which can be very close to each other, but still you need to calculate how much energy you are giving in. Energy will certainly be transferred, but whether that is useful for you or not. So you need to calculate from your temperature range that this is the temperature range at which you want cooling. So you need to do these heat balance calculations to reach out what exactly you're looking at. Now, if you are selecting a phase change material, probably what are the things you are looking at? Certainly high latent heat, because you want a very good backup in a very small volume. You should be able to have a lot of heat or cooling stored in. You also need precise temperature. You want that, hey, if it is, say -19, it should completely freeze at -19 and also completely melts at -19 from, 19.0 to 19.0. But a lot of time this does not happen. So you need to have as precise as possible for your, application. It need to be cost effective, certainly, because, we are in real world where money matters to all. Long retention time, yes, it should have good amount of latent heat, and it should be chemically stable, should remain there, should have good repeatable thermal cycling, so that the latent heat or the performance or the temperature should not drift over a repeated thermal cycling for which you are looking at. Sometimes you're looking at just single time use. Sometimes you are looking at 10 years, 20 years. So you need to figure out what is the thermal cycling you are looking at, and you need to choose the appropriate phase change material for that. Non-toxic, certainly. Non-hazardous to health, certainly you look for, and non-flammable. Most of them are non-flammable, but some are flammable as well. So you need to look for all these key characteristics of the phase change material while selecting. Now, what are the different type of phase change material? So when we talk of phase change material, configurations, it, it can be organic, inorganic, or eutectic. Mainly what you will find is inorganic salt hydrates are something which are mainly used with high thermal conductivity and low temperatures. For high temperatures, yes, when we say low temperature and high temperature, I'm talking of sub-zero and positive temperature application. So in salt hydrate, for all negative temperatures, you get very good property from a lot of salt hydrates. When you go for positive temperature, say +5, +8, +20, +25, 29 for your building applications, yes, there are options of salt hydrates. There are also options of organic. In organic, again, there are two, paraffin based and non-paraffin based, or, bio based. So both these technology exist, and, there are certain challenges in, organic of they have lower thermal conductivity, but this is now addressed with a lot of additives to increase the thermal conductivity. And then you take with the mixtures of organic, inorganic, and organic. So there you get slightly wider temperature range as compared to very close temperature range in case of pure phase change material. When we talk of different forms of phase change material, yes, you can get it into liquid, which liquid and solid transition takes place. So you can fill it into the bottles or plates and then use it. Sometimes you don't want that. If it leaks out, it should not spill over. So then you transition that into gel. So if you have seen the insulin bottles or insulin getting shaped. So you will find gel packs. So these gel packs are essentially water based with gel in it, so that it does not spill as a liquid if it gets punctured. Sometimes it is also soaked in foam, so that it remains stable in the foam, it does not spill out, and then the shape is also maintained. In case of gel, the shape does not get maintained, but in foam, even the shape gets maintained. And in case you want to use for other application like textile or mattresses or something, then you look for powder. So in this powder form, it is micro encapsulated PCMs. So each micro capsule, the sphere, will contain the PCM inside. So we'll talk about it slightly later. So when we talk of microencapsulation, so this is how a typical sphere looks like. It will, heat up when it is at high temperature, and it cools down when it is low temperature, and it changes phase from liquid to solid within within this shell. So this shell remains solid. The core keeps changing phase. So if you want to do a peak shaving in your HVAC, so say for example, when Sandeep Kohli was talking about that, in 9 to 6 p.m. kind of a building, if within the building, if you have PCM installed on your walls or in the infrastructure, then in night time you can actually cool the building and retain that cooling throughout the day. So if during the day you are not able to achieve, or it is expensive for you to cool during the day when the sun is there from 12 to 4 p.m., then you use these phase change material, because in night time it was economical or maybe free for you to cool that and store that latent heat within the building. So there can be multiple applications, but this is just to give you an idea. If you check for the microscopic image, this is how these micro encapsulation spheres look like. They can be in micron size, very powdery. It is very difficult for you to figure out. These are our three commercially available microencapsulated PCMs. First one is OP05, which is for plus 5 degrees centigrade, then 18 degrees centigrade, and 22 degrees centigrade. So 18 degrees centigrade is something which can go into industrial application or maybe data centers, process cooling and all. And 22 is something which goes into comfort and buildings and cooling vest and all that stuff. So you can mix that into your coating and put a coating on your walls. You can mix that into your building material, put that into the plaster or POP or something. So these are all possible. So this is some data about the OP05. So when you look at liquid versus microencapsulated PCM, yes, there is going to be some change in the property. So say for example, the liquid enthalpy, if it was 229 kilojoule per kg, when it is in microencapsulation, it comes down to 155. Same way, it is 229 here, and it comes down to 159 here. So whether you're talking of the cooling cycle, the freezing cycle, or melting cycle, in both cases, the amount changes because the shell is also having the weight. This is for 18 degrees centigrade. So from 243 joule per gram to 181 joule per gram, and then from 244 joule per gram to around 183 joule per gram. This is for 22, which can be used for building. Peak temperature is at 18.6, while freezing. So it from 226 to 160. So 160 is the microencapsulation, and when you're taking the liquid, it is 226. And while for melting, this is 225 to 160 in the microencapsulation. So these are some of the key things They can be used, like conventionally they have been used for chilled food delivery, frozen food delivery, fish transport, replacing ice. Temperature controlled pharmaceutical transport is one of the very big user, where 2 to 8 degree, 15 to 25 degree, minus 15 to minus 25 degrees, so frozen. So a lot of pharmaceutical applications require different temperatures, so it is used. It is also used in chest freezers for maintaining temperature during night time and all. Even on the freezer on wheel, when you see the ice cream carts, so ice cream carts are normally plugged in the night time for 10 to 12 hours, and then for rest of the day they remain unplugged. So there is either the glycol mixture or some kind of phase change material which retains that cooling, so that whenever they are selling those ice creams, they are still solid enough. So not only for cooling or frozen, they are also used for hot food delivery. Say, for example, when you need to deliver pizza at when the in winter, when the outside temperature is +4, +5 degrees centigrade, you need some phase change material or some heating source in the delivery box. Battery cooling, when you see battery cooling nowadays, when you have fast charge and discharge of a battery, whether it is in a phone or it is in car or anywhere, there is some kind of cooling mechanism. Most likely it is going to be the phase change material, because phase change material, when changes the state, it can absorb huge amount of heat. So that is where the phase change materials uses, and some of the phase change materials are also dielectric, so they can be easily you can rest assured that there is no short circuit or something happening in these battery packs. So the cells, whatever heat is generated, the amount of phase change material decides whether how much heat per minute you can absorb into that phase change material. So that's how the quick charging essentially requires phase change materials in this. Now, how these phase change materials are used conventionally in buildings, PCM balls were used. Even today, PCM balls are used. There are a lot of advantages of PCM ball, but there are some disadvantages as well. So PCM ball, when you're using, it is very good to use if it is just water inside, because if any of the PCM ball gets punctured, it is adding into the tank only water. There is no contamination which is getting added to the chilled water system. So if you're using water, it works. If you are not using water, if you're using any other phase change material, then probably you are going to contaminate if any leakage happens, and accessing these balls while servicing is very different. So yes, balls are very good phase change material, but with water filled inside. The other thing is PCM plates. So yes, PCM plates are also used. The PCM plates can be of any size. These PCM plates with a more surface area gives you a better heat transfer, because as the PCM starts to solidify, the heat transfer rates goes down, because solid, the frozen PCM starts to act as a insulator. So if the thickness is reduced, essentially you're getting better heat transfer area, so you're getting better overall heat transfer. So PCM plates are used, but yes, again, there are challenges related to if these leaks happen. Accessing these plate is something where you need to design so that you can easily access. The other thing is also being done is using tubes. So tubes are inserted vertically normally, so that you can pull out tubes from the top if something happens, so you can monitor. But yes, tubes, again, you have better surface area as compared to the volume. So you are able to manage the overall thermal conductivity or overall heat transfer with these. Lot of thermal storage tanks are used with filling phase change materials. So the cooling coil comes in, it freezes the entire tank filled with phase change material, and then the another coil takes care of rejecting that heat. So this is normally how in a HVAC system, if you're not using a microencapsulated, or in the building, if you are looking for a glycol system or a chilled water system, or specifically in a data center when you have high temperature requirement, then having a thermal storage tank with cooling coil inside, then filling the tank with the phase change material is something which is a very good option, being used in a lot of geographies, and probably in India it is still being tried out at certain applications, but I feel there is a lot of room in India to work on these tanks. There can be a single coil in a tank with freezing on the coil and circulating PCM in the cold room. Say, for example, the some portion of this tank gets frozen, rest acts as a brine which goes into the cold room to maintain your temperature. Even it can be used for air conditioning application. Uh, then it can be freezing and melting through the same coil. So you keep this tank as a PCM frozen tank. You first run the chilled water to freeze this tank, and then you run the hot water to take cooling out of this same tank from the same coil. There can be tank with two coils in the tank where freezing and melting happens in the separate. So a lot of things depend upon what are the temperature applications, what kind of solutions you are looking at, and probably getting in touch with, the PCM company is the right solution, so that, they can guide you what PCM works best for, and what would be the best suitable, case for you to use in a thermal storage tank. These are available commercially in tanks, available in bottles, pouches, and all that stuff, and microencapsulation as well. So yes, it is available. It is so PCMs can help business achieve UN sustainability goals, from affordable clean energy, sustainable cities and communities, and climate action. They can be used to reduce your carbon footprint. Unlike other, methods of dry ice and all, these are non-toxic, safe, and easy to handle. PCM offer unique characteristics of maintaining constant temperature for longer time and on repeated cycle. So at BP Refcool, we have a dedicated brand, PCM Wala. There is a dedicated website of PCMwala.com for phase change materials, and we have a lot of phase change materials. So what you see on the screen is a list of phase change materials we have for sub-zero temperature from -1 to -33. They can be used in a lot of refrigeration applications, and these are all positive temperature applications where we can use it from +1 degree to plus 55 degree. So if you look for thermal comfort perspective, probably 20, 23, 25, these are the temperatures which are very good for thermal comfort perspective. So this is all from my side. I feel I'm on time. So if there is any question.
Yes, Kapilji, you are bang on time, and more importantly, the presentation was fantastic. As usual, I'll hand over to Santosh. There are quite a few questions in the chat box as well as in the Q&A box. Over to you, Santosh.
Thank you, Abhiyas. So, Kapilji, first question is about using the PCMs in commercial buildings using chilled water system. So which one is preferred type of PCM? Paraffin, salt hydrate, or eutectic provide the best balance of thermal performance, cost, and long-term reliability? So these three parameters.
I would say this is the wish list. So honestly, the freezing and the melting temperatures normally are the first thing for us to decide. So if we are looking for chilled water, or if we are looking for a commercial building wherein in the building, in the room, on the walls, you are going to freeze and melt, the temperatures changes. So that is what is something which is very important. If you're looking for chilled water system, probably, yes, we are working on development of phase change material for chilled water, wherein we can freeze the PCM at 4 to 5 degrees centigrade, and get cooling out of it from 7 to 12 degrees centigrade. As of now, this work is in progress. We are able to reach around 2 degrees centigrade, but not 4 degrees centigrade. Why I'm saying so, it is important or critical for a chilled water system. Um, you cannot go more, less than 4 degrees centigrade, because if you go less than 4 degrees centigrade, probably in evaporator, you get a challenge of freezing. So you need to invest into a glycol freezer. So if you put a glycol or brine freezer, the entire economics of using the phase change material changes. So if you're looking from a chilled water system for thermal comfort cooling, probably the work is still going on. There are some, which is one of it is paraffin based plus 5 degrees centigrade. But yes, that is something where we need to work, how it is used, whether it is in a tank based or plate or ball based. So, but yes, these are more project specific or your application design specific. If we are talking about the commercial building interiors, then certainly it can be microencapsulated PCMs can be used in coatings on the building materials. It can be used in your ceiling. So a lot of applications are there where it can be used. And they are, all three, paraffin based, bio based, as well as inorganic. All three options are available.
The next question is asking about the material that is the cell is made of the encapsulation. So, what material we generally use for cell preparation during the encapsulation? And the other question is that the thermal conductivity of the PCMs is a bit less, and that slows down the propagation of heat. So, how we can improve that? Is there any changes in the cell material or any other ways?
So as of now, we are using melamine-based shell for our microencapsulation. We are working on some additional, but yes, that is a work in progress. But yes, the thermal properties of shell also matter. I'm not saying it does not matter, but imagine it is a very thin, the entire sphere is like 10 to 30 microns. So, and you are going to spread across the way you are going to use in your application, it spreads across. So the entire surface area is available for heat transfer. So, yes, it is important. But, there are a lot of things when you evaluate this, are more important. Yeah.
One more question is using the possibility of making ice from water during the daytime when the solar is available, and using that ice during night time and melting that to provide the cooling when the evening peak hours for residential sector and for multiple units, if that is a possibility.
Certainly, this is very much possible, and ice bank tanks essentially do that. And it is not new. India or in specifically in dairy industry, ice bank tanks are used. And the only challenge is in ice bank tanks, you need to work with low temperature systems, because to freeze ice, you need to go at least minus 5 degrees centigrade. So yes, if you have those facility, freezing ice and then using that, and there are n number of ways how you can use this melting of ice effectively during the peak hours when the cost of generating cooling is very high. Also, there are the cases which are discussed in India now, wherein you have excess electricity available during the day because of the solar power, but you don't have solar energy storage. So what you do is you freeze ice and use this ice-based cooling in evening when the sun is not there. So you use that in evening to cool your building or people or plant. Yeah. So that is also being used. So yes, if 0 degree water works, it is great to do.
Sir, one more question is on the durability and the number of cycles, basic charging, discharging cycles. So this PCM, the encapsulated PCM. So what is the average range of, like, how many time or how many it can be used
So,
again?
So the microencapsulation is the new one which we have just introduced. So the cycling test is right now going on, but based on the chemistry and the property and the basic, fascial materials which we have used, the basic fascial material we have used goes more than 10,000 cycle. So whether this overall PCM goes for 10,000 cycle or not, it is difficult for us to answer today. But yes, we have very good confidence that since the chemistry and the known properties are something where we are going to get very good stability over a period of time. So we have good confidence, but yeah, the tests are underway.
And what is the derating factor, sir? Like for 10,000 cycles after, what will be the charging?
So if it is more than 10% drop in the latent heat, then we consider it as that, yes, it has derated.
One more thing, one question is that can the powder PCM be mixed in screed and used as flooring screed anyway here?
Sorry.
I can't get it.
So
But
basically, building materials, can PCM materials be mixed in building materials for envelope, wall, roof, and are there any test reports if this has been experimented on, mixing PCM with screed?
So not in India so far, in my knowledge, but outside India, yes, it is being used in building materials, and yes, we are in touch with certain companies who are trying this out. So when I talk of building materials, I talk about the material used in plastering or in the coating or in gypsum board or these kind of applications which are touching the inner surface or the outer surface depending upon what kind of PCM they are using.
one more question is about the controlling the heat rates, heat exchange rates, basically how we reset, how we consume the cooling. Because the temperature dependence is there. So can we control that? Because after encapsulation or before, like we can target the application with the different rates.
I would say that this is something which depends upon the application. So say for example, when you are using liquid PCM and if that liquid PCM thermal conductivity is not enough for you, you want to increase that thermal conductivity, then you use some thermal conductivity enhancers in that liquid which do not react to the PCM. So we normally help either you're using some metals or you're using expanded graphite or you're using something else. So we guide upon that. But that is where it depends upon the application. A lot of time, just by reducing the thickness of the entire, you increase the surface area, you get a lot of the advantages. But if yes, you further need to do, there are options available of using metals or the expanded graphite or something else. Yeah.
So
Maybe one last question.
Santoshji, so AEEE works with well-established industry veterans like you as well as upcoming professionals. So, and I am falling in neither category, but on behalf of someone who has asked this question, so what technical skills should I prioritize to build expertise in sustainable cooling system? I'll ask both Kapilji and Sandeepji to probably one after the other. To a young professional, what would be your advice? Especially someone willing to get into the field that you are dealing in individually. Kapilji first and then Sandeepji.
So, I learn a lot these days from youngsters, and youngsters learn a lot from ChatGPT and other AI tools. So, if you need, I tell you real example. There was one data center customer who approached us that, hey, I have this much amount of tanks with, in data center, you need to have thermal storage. So normally you store water at certain temperature. So, say 18 degree to 25 degree or something. And you need to, to reduce the volume of water, they were evaluating to use phase change material. And I told them that yes, you need to do the heat calculations in terms of I can give you this technical data sheet of kilojoule per kg and temperatures and all that stuff, and then you do the math, and I can guide you. So then he said, hey, you don't need to tell me, let me try and come back to you. So he did it on ChatGPT. He took a technical data sheet from us, put that across into ChatGPT, and ChatGPT made the complete model with his calculation and gave them, and he sent it to me, and I said, yeah, looks great. So probably a lot of engineering thing you don't need to do now. A lot of it is you can learn from industry experts, but nowadays you don't need to go back to you find where you can get access to the knowledge. A lot of knowledge is available. The only thing is you need to filter out and choose what is the right source of knowledge.
And sir, if I may
And
ask on a lighter note, what
yes.
kind of questions are you putting as an expert in ChatGPT?
So, so I personally don't use much ChatGPT, but
Okay.
yes, a lot of our team members do. So when we get stuck on any of the problem, even the core technical issue, we try out with ChatGPT. Sometimes we get very interesting answers, and sometimes not much. But I'm somehow still the old school guy, so don't use much of the ChatGPT.
Thank you, Kapilji. Over to you, Sandeepji. Two-faced question: advice to young professionals. And any discussion today, any forum doesn't end without AI. So probably how much of that are you using in your personal life and your advice to young professionals? Over
So
to
my
you, Sri.
advice to young, yeah. So my advice to young professionals. So I will just give an example of my this present occupation. So I've been in the this field for 30 years. I've been in the job for 30 years. 4 years before that in the engineering. Now, when I joined HMX, I was not aware about indirect evaporative cooling. It was a new subject for me. So what I mean to say that even after so many years in the industry, I still find there are so many new things which are available. And once I found it, then I took it as a higher purpose. So unless until youngsters, if they look for a short term, they may succeed for some time. But unless until you stuck for some higher purpose, because my higher purpose is here is to bring the sustainable cooling, bring the cooling democratically to all industrial workers. We have installed in some industries where people are so happy they were doing welding and they were not having any kind of cooling. So they are blessing us. So I'm saying that money is important, career path is important, position is important, but unless until you have some higher purpose, some kind of your passion with wither out in some time. That is the for the youngsters. So they should always be passionate. If I can be passionate after 34 years in this field, then they should be all the more passionate. They are at young age. But today there are so many distractions. AI is, of course, I would say one of them. Like Kapil said, I am also old school. I also don't use Chat GPT much. But having said that, I'm in my own company. I'm marketing head, so we are using a lot of Chat GPT stuff to find out what should be our brand tagline, what should be our what attracts the masses, because it has to be combination of technical superiority plus what appeals to the market. So there, yes, Chat GPT really helps, and we cannot be outdated, of course.
Absolutely, Sandeepji. The very fact that the passion and dedication that you showed towards preparing your slides and then presenting it today goes on to show the higher calling that you answered to. But thank you for the sake of time, and we want to start on time and end as well. So we are bang at 4:30. So thank you very much, Kapilji. Thank you very much, Sandeepji, my colleagues, Bhairav, Santosh, for facilitating this webinar. More importantly, our very dear audience, comprising of our members and the stakeholders that we have built, the ecosystem that AEEE has built over the last 18 years. Thank you so very much for being a patient and engaging audience. You are the ones who keep us motivated to organize these kind of sessions. We will send a follow-up email connecting all of you over email with the two speakers so that you can take forward your knowledge-centric and business discussions with them. All of you shall also receive an invite for our next Ion Zero webinar soon, and we hope to see you there. If you find synergy with AEEE's work, please do consider joining AEEE as a member organization for your firms and engaging with us under our various programs. With that, I wish all of you a very good evening, and we bring this webinar to a close. Thank you. Thank you very much, all of you.
Thank you.
Thank you. Thank you. Thank you, everyone.
Thank you. Bye-bye.